Okay, so a standing wave is a vibrational pattern where the medium actually appears to stand still while other points vibrate back and forth. You guys have actually seen these a couple times. Some of you are making these with your slinkies. You were creating standy waves with the slinkies in the hallway. The other lab that you guys saw this occurring in was with the strings and the motors that would vibrate at specific frequencies, and you would actually be looking for the different harmonics. Here is the first harmonic in this picture, then the second, and the third harmonic, and we actually were to calculate this. We were actually able to calculate the speed of that rope as it vibrated back and forth. So standing waves aren't really anything new for us, but just some things that are kind of cool that you can do with a standing wave is you can create something called a Rubens tube. And a Rubens tube basically is a tube filled with gas, and they send a sound wave through it, and the gas goes to different heights based upon the pressure within the sound wave. Where you have the node, here's a node and here's a node, those are going to be the low points in the gas, and the antinode is going to be the high point. And when you light that gas on fire, you get flames, and so you have points where the flames are really high and points where the flames are really low. I'll let this guy kind of explain it as well, because this is something he put together. So let's take a look at this video on a Rubens tube.
Let's do a classic physics experiment called the Rubens tube. Now, I really want to bring it down, but it involves open flames, and some people have issues with open flames. So, what we have here is a length of PVC pipe, has about 100 or so holes drilled at half-inch increments, got some foil tape to keep it from melting. On this side, we've got a 2-inch speaker matching the diameter of this 2-inch tube. On that side, we've got some lab tubing leading to some propane. So let's fire it up and see what it does. Alright, as you can see, we got some nice standing flames, a little bit of oscillation from the vibrations in the hose. Let's throw some sound in there and see what happens. Let's start with a 449 Hertz frequency. As you can see, this sets up a standing wave, and we can see, well, the emerging sine curve that represents sound. What happens here is we're having the sound compressing here and not compressing here. The lower pressure here allows more gas to escape into the atmosphere, shaping the sound curve. Now, if we change the frequency, we can see each time we set up a standing wave, we get that sine curve. Higher the frequency, the more waves. Now let's throw some music at this. How about some Dave Brubeck? Now we have real life sound visualization with fire. The Dave Brubeck isn't terribly energetic, so let's try something a little more energetic. Alright, now that's some good physics. I'm going to turn off the gas and have some fun.
All right, cool. That was pretty lit. Let's take a look at the next slide. Again, this is just something we already have kind of dealt with already, but the fundamental frequency is basically the lowest frequency that an instrument can play. And by definition, it is determined by the longest standing wave that will fit within the instrument from node to node. So here's just some pictures of the fundamental frequency of the first harmonic, where you just have half a wavelength fitting within the instrument. Here you have the second harmonic, where it's the full wavelength, third and fourth harmonic. basically, if you can just remember that a standing wave is basically a wave where it appears parts of the wave are moving and other parts are not, you're pretty good. I won't expect you to be able to like draw pictures of the first harmonic or fourth harmonic or anything like that on the test. Another cool example of standing wave is basically taking a look at this Chladni plate. Basically what they do is they sprinkle salt on it, and then they attach it to a speaker, and it vibrates in such a way that the salt creates different patterns due to the vibrations of the sound wave. So let's take a quick look at this video.
The first experiment for the Cymatics music video is called a Chladni plate. Now, Chladni plate's basically a metal plate attached to the top of a speaker. There's sand on top of the plate, and you play different tones through the speaker. The plate vibrates, which forms different shapes depending on the frequency of the sound.
Well, we blew up a lot of speakers with the Chladni plate. So there was a lot of experimenting around the Chladni plate, primarily looking at how much volume we can put through there, how much sand to actually put on the plate, and the different shapes of plates and what different patterns would be created because of those shapes. But what we were really testing was what frequencies create the most interesting repeatable patterns, because that was a key point. So we ended up playing pretty much every audio frequency through the plate to see what different shapes it would form.
And for most frequencies, it doesn't really do much, but when it hits a frequency that resonates with the plate, it forms a really nice pure shape. So we found out what those tones were, and those were the tones we used to draw the plate in the video.
All right, and towards the end of this lecture, I will show you that whole video. It's pretty neat how they basically take sound waves and turn it into various experiments within the video. So stay tuned for that. All right, let's go into our next topic, which is something we talked about a while ago, a few blocks ago, this idea of constructive and destructive interference. Sound, being a wave, demonstrates constructive and destructive interference properties. If you recall, sound waves are longitudinal waves in that they have compressions and rarefactions versus crests and troughs. But you still can have sound waves constructively and destructively interfere with one another. Constructive interference occurs when two compressions or two rarefactions meet up, and basically when they meet up, a louder sound is created. Whereas destructive interference occurs when a compression meets up with a rarefaction, and basically they cancel each other out. I always think a picture is worth 1,000 words. So here's kind of a picture of constructive and destructive interference. Now, it's hard to show compressions and rarefactions, so here they have crests and troughs going on, but in this constructive interference, basically they have two peaks meeting, and so you just get a larger, more powerful crest or trough. And in destructive interference, you have a crest meeting a trough, and you have just sort of cancellation occurring. To show you an example of this, this is a physics professor who basically is creating tones on two speakers, and these tones will create a sound wave, and you will have constructive and destructive interference occurring. This guy is a little bit long-winded when he talks, so be patient with him, but he does a thorough job of explaining what's actually going on. So let's take a look-see at constructive and destructive interference with sound waves.
Okay, this is a demonstration of interference patterns produced by two speakers. This signal generator is generating a tone that's at about 2,000 cycles per second, 2,000 hertz, and it's sending the same signal to both of these speakers. And if you're out in front of those two speakers, then what matters is the distance from you to one speaker compared with the distance from you to the other speaker. If those two distances are the same, then the sounds that are produced by these two speakers overlap and interfere constructively. They add together to form a louder sound. But as soon as you've moved a little bit in such a way that the wavelength, that the difference between the two paths, between one speaker to you and the other speaker to you, is half a wavelength, then instead of the peaks and the valleys overlapping with each other, you get a peak where there's a valley in the sound, and the sound cancels. That's called destructive interference. And so what we're going to do next is to use this microphone attached to this meter and move through the sound field, and you'll be able to see with your eyes on the meter the level of the sound, as well as hear the sound picked up by this microphone that shows this constructive and destructive interference pattern. Okay, right now we have this microphone that's picking up the sound from those two speakers, and we're right symmetrically located in the center between the two speakers. So what we'll do now is to move away from the center, and this readout here gives the loudness of the sound that's picked up by this microphone. And as we move through the interference pattern produced by these two speakers, you'll be able to both hear the sound from this microphone, which will be louder, then softer, then louder again as we move through constructive interference to constructive destructive interference. And then you'll also be able to see that that the readout will show that loud, soft pattern. So I'm going to be quiet now so that the microphone will just pick up the sound from the speakers.